Hi everybody, welcome. It's Mrs. Dunn again. And what we're going to talk about in this screencast is conditional probability. So what we're going to do is specifically in this screencast is we're going to, first of all, I'm going to introduce you to the conditional probability equation, which you should be using constantly anytime you hear that type of problem being asked of you. And we're going to go through two applications, one where we're using a chart and the second one where we're using a tree diagram. So here's the conditional probability equation, and I wrote the words here because I feel like this will help you to understand this if you say it as you're writing it. So the way you would say that equation is the probability of A given B. This line right here means given. So the probability of A given B is equal to the probability of A and B divided by the probability of B. Now let's look at how that's used. So here's an example from the U.S. Food and Drug Administration. So the U.S. Food and Drug Administration was testing the effects of red dye. So an ice cream company wishes to use a red dye to enhance the color in its strawberry ice cream. The U.S. Food and Drug Administration requires the dye to be tested for cancer-producing potential using laboratory rats. The results of one test on 1,000 rats are summarized in the following table. So this table gives you what happened with the 1,000 rats. 60 of them ended up eating red dye and getting cancer, and 20 of them ended up getting cancer and didn't eat the red dye, etc. I'm not going to go through the whole table. But this table does not have the probabilities, and we need the probabilities. So the first thing we're going to do is convert this to a probability table. Since the total number of rats tested was 1,000, if you simply go through and divide all of these values by 1,000, that total, you'll get the probabilities. So this is now our probability table. Okay, so what's the probability of a rat getting cancer given that it ate the red dye? Once again, once I see that word given, immediately I'm thinking about my conditional probability equation. So the probability of getting cancer given that the rat ate red dye is equal to the probability of cancer and eating red dye divided by the probability of red dye. All of those values can be found in the table. So the probability of getting cancer and eating red dye, that's the numerator in this equation, is this value from the table, cancer and red dye, which is 0.06, divided by the probability of the red dye. Well, those rats that ate the red dye is 0.50. So it's 0.06 divided by 0.50, which is 0.12. Let's compare that to the probability of a rat getting cancer given that it did not eat the red dye. So those rats that didn't eat the red dye but got cancer were 0.02 divided by the probability of not eating red dye, which is 0.50, and that probability is 0.04. So you can see how the FDA can make a conclusion based on this information. So what do you think? Should that ice cream company add the red dye? I would say no. There's an increase of about 8%, or yeah, 8% if you eat the red dye. Okay. One other thing I want to show you here is this idea of independence. This comes up a lot in probability. So are eating red dye and cancer independent events? The formula for testing for independence is if two events, A and B, are independent, then the probability of A and B happening is going to be equal to the probability of A times the probability of B. Let's see what happens with our red dye and eating cancer and getting cancer. So the probability of eating the red dye and getting cancer, remember, was 0.06. The probability of eating the red dye was 0.50, and the probability of getting cancer was 0.08. So does 0.06 equal 0.5 times 0.08? And it does not. Therefore, eating red dye and getting cancer are not independent events. That means they are dependent. Okay, switching gears, I want to go and look at a tree diagram. So consider this experiment. So two balls are drawn in succession without replacement from a box containing 3 blue and 2 white balls. Create a tree diagram to show the outcomes of this experiment. So in the first draw, you could draw a white ball or you could draw a blue ball. And on the second draw, you can draw a white ball or a blue ball. Let's look at the probabilities associated with each of those events. So on the first draw, there are 2 out of 5 balls that are white and 3 out of 5 that are blue. Now, if I choose a white ball, then there's 1 less white ball left. There are 4 balls left and only 1 of them is white. So the probability of choosing a white ball on the second draw, given that the white ball on the first draw was drawn, is 1/4. I've written that down here. The probability of the white ball being drawn second, given that the first ball was white, is equal to 1/4. So do you see that those conditional probabilities are actually written right in this tree diagram? So for example, the probability of the second ball being blue, given that the first ball was blue, would be 1/2, or this number 2/4. Okay, one other thing I want to point out is the probability of a white ball being drawn on the first draw and the second ball being white. So what's the probability that the first ball is white and the second ball is white? To find that probability, you're going to multiply this whole path. So the probability of the first ball being white is 2/5. The probability of the second ball being white is 1/4. 2/5 times 1/4 is 2/20, or 1/10 when you simplify it. Okay, so let's look at a problem. What is the probability of drawing a white ball on the second draw? To calculate that probability, you have to add the 2 events where you end up with a white ball on the second draw. So you're going to multiply these, you're going to multiply this path, and add those together. So 2/5 times 1/4 is 1/10, and 3/5 times 2/4 is 3/10. So 1/10 plus 3/10 is equal to 4/10, or 2/5. And that's it. Good luck.